Okay, so we're talking about dynamical systems theory. This is our fourth class meeting, which is pretty remarkable. And today we're going to do some examples of different bifurcations. So a 1D flow is any first order ODE. So we're usually thinking here something like x dot is some f of x. And so if we have some function, if this is f of x, then we see that the flow is to the right in this region over here, to the left of this fixed point, which I'm going to make as a little dot, and to the left here. And so the reason the flow is to the right here is that f of x being positive here means that x is moving to the right because x dot is positive, so x is going to be increasing. And in this region here, f of x is negative, so x is decreasing. So my flow is to the left, and then over here, my flow is again to the right. And so we say that we have two stable, or excuse me, we have two fixed points. A fixed point is any point for which x dot is equal to 0, or f of x star is any value x equals x star where f is equal to 0. And then we have one that's stable. The stable fixed point has flow that moves towards it on both sides, and one unstable fixed point, the flow moves away on both sides. And we can recall that we have linear stability analysis. Which says that if f of x star is equal to 0, then if f prime evaluated at x star is negative, x star is stable. And if f prime evaluated at x star is positive, then x star is an unstable fixed point. And so we can see that just by looking at the slopes. So in this particular curve, the stable fixed point, the one on the left, the function has a negative slope at that fixed point. And now, then the positive slope leads to an unstable fixed point. Folks, good?
Good here.
And now the key is to really think about the idea of bifurcations, right? So the idea of bifurcations is as some parameters change, we have a markedly different flow. So we don't just mean it went a little faster, it went a little slower, this thing happened a little bit differently. The flow is dramatically different. And so in the case that I sort of sketched, right, this first case where, this is some f of x. If I took this f of x, I made a new one. I suppose I made g of x, which was f of x plus some delta, right? And then I say that x dot is f of x plus this delta. As I vary this number, it's possible to use that delta to lift the function up, right? So if delta was some positive number, this would lift the whole function up. And at a large enough delta, right, if my flow now looked like this, if my function looked like that, my flow would be just to the right, right? So if this is f of x plus delta, the flow is now always right. and there's no more fixed points. So we've had a change in the number of fixed points. So this particular bifurcation is called the saddle node bifurcation, or the blue sky bifurcation. There's another name or two for it, but those are the ones that people use the most often. And this particular one involves the creation or destruction of a pair of fixed points one stable and one unstable. Right, so the idea is that by raising this thing up through the tangency point of the function, the fixed points go away. Devin, this making any sense given that you're dropping in?
Well, yeah, I mean, none of this really for me, because like I know I kind of dropped in the fourth meeting, but I'm just kind of running as I go along, and then maybe kind of go back and
think about it. Okay.
Look at this. Yeah.
Right. Daniel, Michael, everything okay?
Good to hear.
Okay, so now one of the things that's interesting is in 1D flows, there's only 3 types of bifurcations that are possible. There's only 3 ways that the flow can change. So the first one, x dot is, say, r minus x squared, right? This is our saddle node bifurcation. And the idea here is, you've got some oh, that's not what r minus x squared looks like. I have the right idea, but so in this bifurcation, we're varying r, right, and we're moving the thing, moving this parabola up and down. So that's the saddle node bifurcation. So that's one of them. The next one of these is called a transcritical bifurcation. And the normal form of the transcritical bifurcation is x dot is rx minus x squared. And here we're thinking that r is some number and it doesn't have to be anything in particular, right? So r can have either positive or negative values. And in the transcritical bifurcation, let's think about the fixed points. Well, so I need f of x is r times x minus x squared, which means it's x times r minus x, right? If I factor out an x, that's what I would get. And so the fixed points, f of x star equals 0, those happen at x star equals 0 and x star equals r, right? So at either r or at 0, I have my fixed points. Good? Everybody okay?
Doing right here.
So I always have 2 fixed points, but the nature of those fixed points can change. So for instance, when r is negative, then x dot is rx minus x squared, looks like this. And I have a stable fixed point at the origin and an unstable fixed point here at r, right? So r is negative here. And so at some negative value of R, I have a unstable fixed point. If R is 0, this curve just becomes minus x squared. And in that case, the flow is always to the left, and the origin is the only fixed point, but it's metastable. It's stable from the right and unstable from the left. And then if R is positive, now the curve looks like this. And so the flow is in this way. And so the fixed points have changed. The fixed point at the origin has changed its stability. See, there's always two fixed points, but the one at the origin changes its stability. If you notice here, there's always two fixed points, except for in the case where they've merged, right? So the R equals 0, one instant they've merged. The stable fixed point's always on the right for this flow. All right, so I'm using this flow for all three graphs, right? But for different values of R. So the stable fixed point's always on the right. But as I change R from a negative number to a positive number, the fixed point that's at the origin goes from being stable to being unstable. So that's a change not in the number of fixed points, but in the character of the fixed points. And so again, we can draw our bifurcation diagram. We can plot R on this axis and the fixed point location on that axis. And when R was negative, the origin was stable. See, the origin here is a stable fixed point when R is negative. The origin continues to be a fixed point for R positive, but it's unstable. So this dashed line means that the fixed point that's at the origin is unstable. And then my fixed points were at x star was 0 and x star was R, right? So x star equals R is a line. But when R was positive, that fixed point was stable. And when R is negative, that fixed point is unstable. So this is my bifurcation diagram. This is my bifurcation diagram for the transcritical bifurcation. So I always have two fixed points. The one at the origin is stable, the one at the when R is negative, and when R is positive, the one at the origin becomes unstable. And again, the way to read a bifurcation diagram is you drop a vertical line somewhere. That vertical line corresponds to a certain value of R. So R is some dial that you're turning. It's how much power you're giving the system. It's, you know, the capacitance on a variable capacitor. You're changing the capacitance, right? So R is some physical variable that you're manipulating in the system. You let it settle down, you see what the fixed points of the system are. Then you move it to a new value of R, you see what the systems are. So if I draw a vertical line, I've set up a particular system. And for a positive R value, I have a stable fixed point at a positive X and an unstable fixed point at the origin. Whereas if I drew a vertical line over here, that would be a negative R value. So I've turned my dial to some other R value. And I have a stable fixed point at the origin and an unstable fixed point at negative R. That's what makes sense.
Yeah, I'm following that.
Okay.
Yes.
All right. So now the last type of bifurcation that you can have, are things called pitchfork bifurcations. Oops, that's not where I wanted to put that page. No, let me do that. Cut. Now, pitchfork bifurcations are one type of thing, but they come in two different categories. They come in a category called supercritical and subcritical. So the supercritical pitchfork, and the subcritical pitchfork bifurcations are the following things. So now I have x dot, so this is the supercritical one, is rx minus x cubed. Okay, now, I can factor out an x again and write it that way. Yep, everybody okay with that?
Good dear.
Okay, so now f of x is x times r minus x squared. So the fixed points are at x equals 0 and r minus x squared is equal to 0, or x squared is equal to r, or x is equal to the square root of r, plus or minus the square root of r. So for this system, if r is positive, I have 3 fixed points at x equals plus root r, x equals 0, and x equals minus root r. And if r is negative, I have 1 fixed point. I only have x equals 0, right? Because I can't take the square root of the negative number. Okay. Everybody good? So if I draw out x dot versus x for r positive, what you get is a curve that looks like this, right? So x dot here was rx minus x cubed, right? So here, if x goes to plus infinity, x dot goes to minus infinity because of the minus sign there, right?
Professor Kling, can I just
Yep.
ask, for the r is greater than 0, for the third fixed point, is that negative, the square root of -2?
No, it's supposed to be an r.
Okay, I was just making sure.
So now my flow here looks like that. Okay. So for my, am I still with you guys?
Yes, there you are.
So for my positive r, I have a flow where the x equals 0 is unstable, and the x being plus or minus root r are stable. Now, if I do r negative and I just sort of sketch what it looks like, it ends up looking kind of like that. And so there's only 1 fixed point at r negative. This is x dot is rx minus x cubed, but for r negative, you get a function that looks kind of like that. And so now x equals 0 is stable. So if I go and draw a bifurcation diagram, So remember the definition, what a bifurcation diagram is a diagram where you plot the fixed points against the parameter. Plot the location of the fixed points versus the R parameter, the parameter that you're doing. So now when R was negative, I only had a fixed point at the origin, and the fixed point at the origin was stable. But when R became positive, this origin stayed a fixed point, but it became unstable for positive R. But now I had branches that came off this way that were stable, and these branches were at plus root R, and this is at minus root R. So this is my bifurcation diagram. Why is this called the pitchfork bifurcation?
It's a pitchfork.
Because it looks like a pitchfork,
Yeah, it is a pitchfork.
right? You could shovel hay with this, right? Looks like a pitchfork. So this is our supercritical. So this is x dot is rx minus x cubed, and this is called the supercritical pitchfork. So in the supercritical pitchfork, there's either one or three fixed points. One of the fixed points is at the same place and it changes sign, it changes stability, and a pair of fixed points of the original stability appear. So if I start at negative R and I turn my dial up and get to positive R, my origin was unstable at negative R, say out here, right? And as I bring my parameter up, the origin becomes unstable and these two other stable fixed points appear around the origin. That makes sense?
Yep.
Okay, and then there's something called the subcritical pitchfork. And you could intuit that that's simply going to be the reverse situation. So if I have R versus X star, in the subcritical pitchfork, what you typically have is something which is stable here. Oops, no, that's wrong. All right. Yeah, no, that's okay. Becomes unstable, and there were unstable branches off this way. So this is now the normal form for this is x dot is rx plus x cubed. And yep, so anyway, so what you end up with is becomes x times r plus x cubed. So the fixed points are at x equals 0 or x equals plus or minus the square root of negative r, which is why I'm over here on the left. And then you can see the minus r means that I'm over here, right? So this is plus root of minus r. And then if you do the linear stability analysis or you plot it, you can see that those are unstable fixed points. So that's our subcritical pitchfork as opposed to the supercritical pitchfork.
It should be x squared in the parentheses up there, right?
Yeah. That's x squared. Okay. So the game then is to sort of, if you have different flows, any flow you write down can only have one of these three types of bifurcations in it, right? So if you write down some random flows, now if we look at the homework, 3A, say, let me just pick one. X dot is Rx plus X squared. Really? Did I really mean to do that one? Okay. Oh, these are some fun ones. So let's suppose I have that one, okay? So the question is, where are the fixed points? What type are they? And what bifurcation do I have? Right. So if I'm doing this one here, so for this one now I'm saying that f of x is rx plus x squared. So that's x times r plus x. Yeah, okay. So that means that the fixed points could be at 0, and the fixed points could be at minus r. Right, so I'm setting f of x to 0, and solving for x, I get 0 and minus r. That good?
Yep.
Now let me do f prime. So f prime is r plus 2x. Good. Think so.
Yep.
Yes.
Okay. Okay. So now the reason I do that is if I compute f prime at 0, I get r. And if I compute f prime at minus r, I get r plus 2 times minus r, I get minus r. Now remember, what linear stability analysis says is that if the derivative is positive, the fixed point is unstable. And if the derivative is negative, then the fixed point is stable. So I have these two fixed points. I always have two. So I always have two fixed points. But I see that if r is negative, x star equals 0 is stable because of this, because f prime is equal to r. And x star equals negative r is unstable. And then if r is positive, it's the reverse. X star is 0 is unstable. And x star equals minus r becomes stable. And so if I draw my bifurcation diagram, when r is positive, the origin is stable. When r is positive, there's a fixed point at negative r, and that one is unstable. Everybody see what I've done so far? Except I did it wrong. You should be confused. Did I do it wrong? Okay. If r is positive, now I'm looking at r as positive, the origin is unstable. Woo! Now I'm doing the right thing. And if r is positive, then the one at x is minus r is stable. So I've got that. So now I've got something that's good. That look better?
Yep.
And then this one is unstable and that one's stable. So this is a transcritical bifurcation. This one's going to have a transcritical bifurcation. Good.
Good.
Did anybody try any of the homework? Want me to do one? A particular one, or just do another one?
Number 4 was interesting to me.
Okay.
That was the
Number-
one with the natural log.
4 says x dot is Rx minus the natural log of 1 plus x. Okay, so I'm going to define f of x to be Rx minus ln of 1 plus x. I need to solve 0 is equal to Rx minus ln of 1 plus x. So that means that Rx is equal to ln of 1 plus x. And now I get to this point and I go, okay, I can't do anything else algebraically with that. Right? There's nothing I can do algebraically to solve that equation. So what I'm going to do instead is I'm going to plot both sides. The ln of 1 plus x is it blows up in the negative direction at ln of 0, right? Ln of 0 is minus infinity, right? Everybody agree?
Yep.
Is there something wrong with this problem?
I was confused a little bit by it, but it was kind of interesting.
Yeah. What did I do? Oh, that's interesting. Oh, that's interesting. I actually didn't bother to do it this way in my solution. Let me back up a minute. So before I graph it, well, okay, no, fine, I'll graph it. So Rx is a line. So this is Rx. And if I change R, I just change the slope of that line, right? That line always goes through the origin. And changing Rx just changes the slope of the line. Yeah, everybody good?
Yeah.
Yep, good with that.
Now, the ln of 1 plus x at x equals 0, the natural log, so the natural log of 1 is equal to 0. Right?
Yep.
So the ln of 1 plus x goes through 0, 0. And then it blows up at x equals minus 1. It's coming off of infinity down here. Agree? And it goes through 0. It's going to do something like that.
That's what I had drawn.
Right? So as I change the line, so what I can play with is the slope of this line. There's some value of R. So the blue curve stays the same always, right? The blue curve always does that. There's some value of R where it's tangent. And there's going to be some value of R if it's sufficiently shallow. There'll be some value of R where it does this. So at small r, there's two fixed points. One's on the right, one's at the origin. At large r, there's some value. There's some. It not making any sense, right? It's at the origin and on the left.
Yeah.
That makes sense?
Yeah,
Okay, so
I'm following.
So there's two fixed points. So that seems to imply it's going to be a transcritical bifurcation. So the three types of bifurcations are the saddle node, where you go from none to 2, the pitchforks, where you go from 1 to 3, and the transcritical, where you always have 2, but they change what they do. So this is going to have to be a transcritical bifurcation. And so if I want to think about what's happening at the origin, so at one of the fixed points is always x equals 0. So f of x was rx plus the natural or minus the natural log of 1 plus x. So f prime is r minus 1 over 1 plus x, the derivative of the log of 1 over 1 plus x. The log of 1 plus x would be, put the whole thing underneath, take the derivative of 1 plus x, you get 1. Everybody buy that?
Yes.
Okay. So that means that f prime at 0 is r minus 1 over 1 plus 0 is r minus 1. So if r is more than 1, then the origin is unstable because f prime at 0 is positive. And if r is less than 1, the origin is a stable fixed point because f prime at 0 is less than 0. And if r was positive, or if r was big, then there was a fixed point at some sort of negative value, which is stable. And then you can intuit here that the fixed point at the positive value is going to be unstable. So I've got x dot is rx minus the natural log of 1 plus x. Okay, now this is sort of the power of dynamical systems theory and thinking about things geometrically. This differential equation is a crappy, shitty, ugly looking differential equation. That would be really hard to solve. Okay, so to find x as a function of t, yuck, god awful difficult to solve, right? But if r is positive, no, excuse me, if r is a number more than 1, if r is any number more than 1, I know that there's going to be a fixed point at the origin, which is unstable, and a fixed point over here that is stable, and the flow, oops, that's not the right direction. I'll move it over a little bit. It's going to look like that. And if r is smaller than 1, so if 0 is less than r is less than 1, then the origin is a stable point, and there's some unstable point out here, and the flow looks like that. And so I know what this differential equation does, even if I haven't solved for x as a function of t. That makes some level sense?
Yep.
Okay. So now, let me try to let's look at the 3B homeworks. and find one of the pitchforks. So we can see how a pitchfork works. Okay, so let's grab one. So let's do X. So this is homework 3B. Well, let's find one that looks fun. Rx minus the sinh of X. So that looks ungodly horrific. Right? So we got X dot is Rx minus the sinh of X. So f of X is Rx minus sinh of X. Okay, so I can't solve that algebraically. So what should I do? I want to set that equal to 0. So what should I do? When you can't solve something algebraically and you don't have a computer around, what do you do?
Graph it.
You graph. You don't just graph it, right? But you graph both sides. You set Rx equals sinh of X. And so the sinh, I'm going to keep, see, one of these has a parameter. This side has a parameter in it. So that's a line with slopes that vary. The sinh of X is e to the X minus e to the minus X over 2, right? That's the sinh. People remember that? Maybe, maybe not.
Not
Looking
really.
it up this morning, yes, but
What's that? Yeah. So at positive, so this thing here, let's see, what does it do? When X goes to infinity, this term wins. And so it's going to get big out here. When X is 0, it goes through 0. So it goes through 0 somehow. And when X goes to negative infinity, this term wins because so it's got to do something like that. That sound right? Everybody buy that?
yeah, I looked up the
Or it
cosage.
looks something like that, right?
Yeah,
So now, if R is small, then when I plot this side, if R is small, I'm going to get one root. That makes sense? But
Yep.
if R is larger, I'm going to get 3 roots. See, because there's 3 intersections of the black line, the blue curve. So this is some kind of pitchfork. Everybody buy that?
Yep.
Okay. Now, so how do I figure out what the flow looks like? So now let me do this big R value. So let's do large R. I'll grab a red pen here, right? So here's my axis. I'm going to have large R. So at large R, out here, there's a fixed point here, there's a fixed point here, there's a fixed point there. So those are my 3 fixed points, right? At large R, if I'm to the right, if I'm over in this region over here, right? if I'm at big X values, the cinch is more than Rx. So I'm out here where the black curve is my cinch is more than Rx. So I've got Rx, that's the blue line, minus the black line. The black line is bigger than the blue line. So when I subtract the black line from the blue line, I get a negative number. So out here, the flow is that way. Should I go through that again? Let me go through the next section. So I'm going to pick some value of X in this region. So let me pick this value of X right there. At this value of X right here, the blue line, which corresponds to Rx, is more than the black line. I'm going to get rid of my X small line, my R small line. So I'm going to get rid of my R small line. So I only have these lines to work with, right? So at this value of X right here, that value of X, the blue curve, which is the first part, is more than the black curve, which I'm subtracting from it. So at that value of X is in here, my flow is to the right. Whereas when I get past that fixed point, my flow is to the left. So this fixed point right there is a stable fixed point. People buy that?
Yep.
And now
Good
the
here.
same sort of argument goes over here. I'm going to end up flowing that way. And we're going to end up flowing that way. So this is going to be a stable fixed point. That's going to be an unstable fixed point. So at large R, I end up with two stable fixed points at plus and minus something or another. And then if I have a smaller R value, so if I come down here and I draw this for small r, so now if I take out this curve, and I put in some curve like that. Now I only have one fixed point. It's only at the origin. And if I'm to the right of the origin, my blue curve, which is my Rx, is less than my cinch curve. So my flow is going to be towards the origin in both cases. And this one's a positive fixed point, a stable fixed point. Okay, so this is now a supercritical pitchfork, because it went from having one stable fixed point at the origin to having an unstable fixed point at the origin and two stable fixed points prongs. Everybody good so far?
Yep.
But I can do one more thing. I can find the value of R for which that happens. See, there's a value of R for which Rx and the cinch line up. So here's the cinch, right? So this is the cinch of X. So that again was e to the X minus e to the minus X over 2. All right, so now d by dx of the cinch of X is the cosh of X, which is e to the X plus e to the minus X over 2. And at X equals 0, the cosh of X is 1, right? Because I would have e to the 0 plus e to the 0 over 2 is 1 plus 1 over 2 is 1. Okay, everybody happy with that? That makes sense?
Yeah.
Yep.
So that means that the tangent line to the cinch of X has a slope equal to 1 at the origin. So the value, so if I go back to X dot is Rx minus the cinch of X, at r equals 1 is where I have x dot is x minus the sinh of x. And that's the limit before I get 3 fixed points. So if I go and try to draw the bifurcation diagram, I'll get a pitchfork, right? If I draw r versus x, when r is 1, anything for r anywhere less than 1, the origin was a stable fixed point, and then after 1, the origin became unstable, and I have 2 stable fixed points around it. So I can find where the locus of the pitchfork happens. The locus of the pitchfork happened at the parameter value r equals 1 in this case. That makes some level of sense.
Yeah, I kind of followed that.
Okay, so you can figure out which parameter value. So I've got this function I'm working with, right? I can figure out which slope just grazes it. And then after that, you hit it 3 times. So if it's shallow, 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 it only hits it once. It hits it at the origin, but there's a slope for which it just becomes tangent. And then after that, it's going to hit it 3 times as I vary my arm. Okay, so this is what we can do essentially with one-dimensional flows. One-dimensional flows can't be chaotic. One-dimensional flows can't do anything too exotic. The only thing they can do is have bifurcations. And the bifurcations have to come in one of these 3 varieties. There's no other variety of bifurcations in one-dimensional flows, which is also kind of an interesting thing, that there's a very limited number of ways the system can change. Even if the function looks wacky, it can only do one of 3 things, is sort of the lesson in 1D flows. So the next step really is to go from one-dimensional flows to 2-dimensional flows. And so now you would have one second order differential equation, or 2 first order differential equations, or 2D flows. And so that's maybe what we should go and do next. Sound good?
Sounds great.
So you folks can like play around with these homework problems. Devin, do you want to get into the Blackboard site where you can like look at these homework problems or see the notes or anything like that? Or do you just
Definitely.
now and you're here today?
Sure. Yeah, I'm assuming you have the recordings of these lectures on there too.
Yep.
As well. Okay,
Yep.
cool.
So I'm going to stop recording here, and I'll see you folks next week.
Sounds good. Awesome. Thank you.